Hello everyone, welcome to All Things Indian Friendly Voices. This is episode 10. Today we are going to discuss modern mathematics in higher education in India. Mathematics is something which has been probably we can trace back the history of mathematics, the origin probably ever since human beings started settling in communities. Probably it all started with inductive logic, counting, and etc. etc. As the time progressed and the requirements of human society became more complex and refined methods and more higher understanding was required, and mathematics also progressed across civilizations. But mathematics is something which most of the Indians, all of us, including me, we all study in school. After that, we get disconnected from mathematics directly. And for many years, in fact, for majority, after 10th standard, they don't pursue mathematics at all. So we don't know what modern mathematics is, what are the developments in mathematics, and what is the philosophy of mathematics, and what is the status of teaching mathematics in India. So majority of us are in dark. Since the aim of this series, objective of this series is to take uh, almost whatever the subject we take to the masses. That is our objective. And today we have chosen modern mathematics, something which most of us have zero knowledge of, including me. So to discuss this and more, we have two wonderful friends with us today.
Yeah, thank you, Rajman. Let me introduce you to the panel of today. These are two good friends, Dr. Vasant Srinivasan and Dr. Arul Selvan, and welcome to both of you. So let me give a brief introduction about both of them. First, Dr. Vasant Srinivasan, he did his PhD under the supervision of V.S. Sundar at Indian Statistical Institute. And while he was doing his PhD there, Dr. Sundar moved from there into Indian Mathematical Science Institute of Chennai. So Dr. Vasant moved to Chennai then as a PhD student. After that, he did his postdoc at Harishchandra Research Institute at Allahabad, the University of Orleans in France. For a year, he was a postdoc. And then for 2 years, he was at the University of Tokyo. Currently, he is a faculty at the Chennai Mathematical Institute, and he's been there from the year 2006. His area of interest is basically operator algebras. He initially worked with the subfactor theory. This was an area of mathematics which was initiated by Dr. Vaughan Jones, a field medalist who had died recently. Then he shifted to the study of E0 semigroups. Currently, he's working on quantum information theory, and he's also giving courses on quantum computation, though he has not actively started working on that area. Now, coming to Dr. Arul Selvan, he's an engineering researcher with a lot of academic training. He did his BE and PhD both from Indian Institute of Science, Bangalore. His specialization was in understanding the mechanics, deformation, and physical phenomena at very small scale, at small scales. Now, after his PhD, he was a CEO of a development company, development center for a Japanese multinational company. Their focus was on developing design and automation software. He is currently residing in Bangalore, and his current interests are automating agricultural farms. And he has been someone who has been following the curriculum and the teaching of mathematics and physics at school and college level. Dr. Vasant lives in Chennai. Now, we are good friends on social media and outside of it. So while we discuss, we may drop the doctor prefix sometimes, so don't mind that as we are. And one trivia which I want to tell was that I happened to stay in the same hostel room as Arul Selvan. After he vacated it, the next year I was there. Though we have both not met in IAC, we have came to know each other much later. So once again, welcome to both of you to the show, and it's an honor to have both of you here. So I'll request Rajmohan to start the proceedings by asking his questions on mathematics.
Thanks, Suresh. The biodata was really frightening for a math atheist like me. At least until the last bit you came, you said automating agriculture. Okay, something which we can, at least I can tangentially see. We'll start with Vasant, and then Arul can add. So my first question will be very fundamental one. So what is modern mathematics? Because as I said in the beginning, most of us, majority of us, are not aware of what this modern mathematics is, and later the axiomatic treatment of mathematics. So for the benefit of people like me and millions of people out there, can you please explain what modern mathematics is?
Okay, so I will go a bit detailed. I mean, I will take some time for this question. So, okay, what you say is absolutely right that many people don't have a good idea about mathematics, which I have encountered everywhere. I mean, so it's not just, I mean, it's not something about whoever you call us ordinary people or something. Even with people who have some intellectual accomplishment. So even with them, I have found that they haven't understood what is modern mathematics or what it means by research in mathematics or something. You know, once a doctor asked me that when I was describing my profession, I'm doing this or something, then he asked me, "Oh, I mean, people do research in mathematics. I don't understand," or something like that. In fact, two doctors told me like that. So and it's not just that. I mean, I have encountered in Twitter. I mean, when, for example, once I was talking about some literary text, and someone was, it was something contradicting view. I had several fights in Twitter, and it was something to ridicule me. One person said that, I mean, it's not about that. It's something that the point he was trying to make is, it's not some mathematics where you can apply some formula or something. Literary text is not like that. So the idea is, I mean, it's like with some concrete opinion, you can approach this or something like that. So, so there's a general opinion that it has something to do with very concrete. I mean, even last week I read a post on NEET. So it's about NEET, but the post is, I mean, I agree with the post. That's not the point. But there, finally, they said if we have entrance exam for everything, then it becomes like something like. Then it's all mathematics. You have to memorize and you have to apply formula, something like that. So that's the idea generally people have. It's like applying formula. Or when some people, when I say I'm doing research in mathematics, some people will ask me that, so will you invent new formulas or what is that? So that's the basic idea many people have. So maybe one should. I mean, I'm not offended by any of these things, but it's a little bit provoking. So I should say that first. I should say that mathematics is one of the most creative space, and it's any creative space like any literature or anything. It's a highly creative space. So it's like in math, in literature and other things, people create some reality. Some reality is created. Math also creates a reality. And it's a completely different reality. It's a mathematical reality. And I mean, even in literature, people do some sort of, I mean, maybe if it's a magical realism, you do a magical manipulation of the reality or do something with that. But math is something, it's a completely extending this reality. Whatever we have, this reality, it extends the whole reality. And it has been done in a very rigorous way, in a very precise way. And it is done without any contradiction. So, I mean, it's a very, I mean, that's what I mean by precise, rigor, and all those things. So what is this kind of, I mean, what is this rigor or something? So when I say something precise, I mean, it's a framework where we create new things, new reality, mathematical reality, and we create new objects and work with that. And so the first thing is, it's a very rigorous framework. So in the rigorous framework means what you do is first we say make the statement very precise. What does it mean by precise? Means you cannot have two interpretation of a statement. There should be only one interpretation. Like literary text, we can have many interpretations. So by this, I don't include the wrong interpretation. Okay, Okay, I mean, it can be, one can say that, okay, I don't know mathematics, I interpret it like this. That's not the point. So those those problems due to human understanding, that we exclude that. I mean, we are not talking about that. Suppose there are experts, you have to assume that. Suppose there are experts who understand mathematically. There are questions that mathematician can make mistake and other things. I'm not talking about that. When there are experts discussing some mathematics, then for a statement, there should be only one interpretation of that. So how is that possible? So one reason is there cannot be two reasons. There is something like there has to be a negation of a statement. For example, the reason is how do we say there is only one interpretation? It should never, for whatever you do, however you argue, however you deduce any further statement, you should never end up in a contradiction. Okay, you cannot have any conflict. So for that, the basic condition is, you should, if you have some statement, there will be a negation of a statement, and the negation of that negation should be the original statement.
Okay.
So that will make sure that you will not end up in this contradiction. Okay. So you have a statement, then you can make a precise negation. Of course, I'm only explaining what is a precise statement. So you can make a negation. Negation is an opposite statement. Then the negation of that negation should be the original statement. You should get back the original statement. So that is what we say, that it's a very precise, rigorous framework. So in a sense, that it is the only framework where I would say that the rationality works completely. In its perfect form. So it's like anything is rational when you use a mathematical framework. Physics is rational because the language of physics is mathematics. When they write things in mathematics, then it becomes really rational. So you can even say that mathematicians are the only rational people or something. It's true when they do mathematics, but mathematicians can be equally irrational when they don't do mathematics. Maybe more irrational. Indeed, most of them are also. I have found them, most of them are. So that's the one thing. So what I could say is the definition of mathematics can be, it is the any approach to anything, any rational, any logical approach to anything, which can be done in a very rigorous framework, can be called as mathematics. But then in the human history, mathematics hasn't, there are not many mathematics. There's only one mathematics. There are, if you do something else, that's not everything is accepted as mathematics. So there are some few axioms which are accepted by all mathematicians. So that's accepted throughout the mathematics. So those things I want to explain that later. So, but then the mathematics has something to do with reality. It's not something comes out of somewhere else. It has something to do with reality. It is out of this reality we just produce this mathematics. But then mathematics is not real. Whatever the mathematical objects or something we see, it's not real. For example, you take any number. For example, you take the number 3. There is really nothing like number 3. You can say there are 3 apples. You can say there are 3 writers. Jay Mohan, Charani Vaidata, Ramakrishnan, everybody knows. There are 3 writers in Tamil. So there is something common between 3 writers here and something common between 3 apples. Common between 3 writers and 3 apples. What is that? Then you get the notion of a set. You have a set of 3 writers, you have a set of 3 apples, and both have same number of elements. That's all. So there is a cardinality. So you need to define 3. You want to talk about 3. So in this real world, there are only 3 apples, 3 writers, 3 planets, 3 something. But there is nothing like number 3. Number 3 is a mathematical imagination. There is nothing like number 3. And it's not just the number 3. Okay, you can think that number 3 is actually there in the reality, but it's like 3 apples are there. So number 3 is there in the reality. But there is something called any real number or something. For example, a fraction. You cannot explain what is a fraction, for example. So, for example, you want to say what is half. You will say that if you have an apple, then you can cut the apple into half and you can say that it's a half apple. But then there is really nothing called, you cannot make a half apple actually, precisely. It's not possible to do. For instance, let me say that, suppose if you associate a real number, any real number, 3/4 or even irrational or irrational, any real number with the length of something, then in reality, there is a length does not exist. We may not realize that. For example, if you say something has a length of 1 meter, it can never be precisely 1 meter. Let me explain why it is true. I mean, the 1 meter is actually a construction of somebody. I mean, I'm coming to that why the mathematics. I mean, it's deal with something completely not something reality. It's a kind of. For example, if you take something as if you have a line with 1 meter or something, that will be a problem. For example, if you take a line with 1 meter and to take another line with 1 meter, okay, you form a right angle triangle. Okay, then you have the Pythagoras theorem, which says that the length of the hypotenuse has to be square root 2. But square root 2 is an irrational number. So if you want to measure that length, it's going to have infinite decimal. That's what it means, infinite decimal with there is no recurring, there's no periodicity, you can never guess. And it seems that it's just clear that you can never measure that hypotenuse. But then 1 meter is just our construction. You can take that hypotenuse as 1 meter, for example, and you can define that to be 1 meter. So there is really nothing called the notion of length in our reality. You say 1 meter, but it's very approximate. I mean, there is really precisely, you cannot talk about any length to be precisely this real number or something. So real number is something completely imaginary. I mean, it's a completely a mathematical reality. In reality, we don't have a real number. It's not, I mean, you can say that number 3, number 4 is there because there are 3 apples are there. But then there is no real precise real number, any real number. I mean, there is no way we can connect to reality for a real number. But it is constructed from, I mean, you have number 3. Using number 3, you can consider fractions. Using fractions, you can consider all so-called rational numbers. Using rational numbers, there is a way of constructing all real numbers. It's all mathematical construction. It's not anything to do with reality. I mean, if you want to think, there is no really a straight, you can form 2 points and you can talk about a line joining 2 points. There is no infinite line, for example. I mean, it's a mathematical thing. There is no infinite line or something. So in a sense, the mathematical thing is, it's a kind of, you see something in reality, you formulate it in a mathematical in a framework, and then you extend it also. See, in mathematics, for example, we live in a 3-dimensional world. We all think that it's a 3-dimensional world. Then you must have studied some coordinate geometry where you have seen that, I mean, Euclidean geometry, where you talk about x-axis, z-axis, y-axis, z-axis, which represent a 3-dimensional space. But then mathematics, there's no need to limit to 3. There is nothing special about 3. I mean, you can have n dimension. When you have n dimension, you can in fact think about infinite dimension. And you can study the same geometry in n dimension, or you can go to infinite dimension. Then you can put more structure on it. It's just not, I mean, there are some structure in the reality. You have to get analogous structure on the infinite dimension space. And there the geometry will be completely different. And you form something called Hilbert space, Banach space, I mean, whatever, I'm just saying some names. So there are many new objects you can create. And those objects will have relevance somewhere else. I mean, it's just, so what I'm saying is, the whole thing is we can create some new objects. It's a completely kind of new creative thing where you create a new reality where, I mean, it looks like whatever you do in, not whatever we do, but whatever mathematically you can do in 3-dimensional space, you can do in infinite dimensional space. So mathematics can create such a reality. So it's a completely, there is a word in philosophy which I don't remember. I mean, so to call this kind of statements and the reality where we make. So which I don't remember, which I can Google it. I mean, anybody can Google it out later. So it is just, so traditionally mathematics has something to do with computing and calculating, but modern mathematics is about creating new objects through this in this rigorous framework. So that's what I want to call as modern mathematics. So I want to say, I mean, it's more connected to logic. I mean, it's more connected to logic than computation. But then it was not a very recent, I mean, modern mathematics starts from, it's there from last 100 years or something. But then it was not something, the mathematics connected to logic very recently or something. Even in the Greeks, there is a difference between whatever we have done in a way. I mean, every culture has mathematics, but there is a difference between what other cultures have and what Greeks have been doing nearly 2000 years back or 2500 years back, what they were doing. They were doing here mathematics. For example, in India, they say they know this thing, that thing. Of course, there are many wrong things also, wrong things attributed. But there are some real, actual things also Indians know about it. But then that is connected to some religious ritual or something, and there they are some for trade reason or something. The Greeks were the one, they were really studying mathematics as a part of philosophy. Even they had logical proofs, and at the time itself, they have talked about logical proofs and other things. So they were the one who talked about, even Plato has long treatise on mathematics and everything. So they were the one who started mathematics. But then usually mathematics is something to do with computation or it's basically, maybe there is something to do with geometry or general computation with numbers, solving equation or something. So there is a general way of trying to define mathematics as some study of pattern or symmetry or whatever we see, and trying to formulate it, quantify it and formulate it. That's what people call as mathematics. But the modern, whatever the modern mathematics, in my opinion, modern idea of mathematics starts from, that is not the modern idea of mathematics. The foundation or the seeds for modern mathematics comes from calculus, I think. Because the calculus has the notion of limit, for example. So the important thing is there is a limit. Once you have to talk about limit, you have to talk about the distance function. You have to have a notion of distance. We know what is distance, but a precise notion of distance is needed. And when you want to talk about limit, so the limit is something goes to something when something goes to this. What does it mean? This is as close, when you can make that as close as possible, as close as you want. When this is as close, when this is made as close, necessarily close. When this is, you can make the other thing very close. If this is made some reasonably close, then we can make that close. So this kind of notion of limit is something which has the very rigorous notion. So this kind of rigor and logic starts from calculus. There is an epsilon delta definition for this limit, which was not actually, I think it was given later. It's not by Newton invented calculus, people say, but people say it was there in India and it has been accepted also. But then the kind of rigorous calculus comes later. So I think that this calculus is where the rigor for mathematics starts. Then there is, the Newton starts, and Newton and Leibniz, I think. Newton, Leibniz, Euler, Lagrange, and it starts with, then the foundation, the mathematics is founded. But then the point is, if you have some structure, the idea of mathematics is, if you have some structure, if you have some collection of functions, they share a property, then you generalize that property and make a new object. Completely, even as I said, the three real numbers, they are all mathematical objects, which are completely, which has something to do with reality, but they are not real objects, mathematical objects. But using that, you create completely abstract new objects. And you study that, and you cannot just make statement about these objects. You can make a general statement which will be used everywhere. For example, one of the basic problems in traditional mathematics is solving equations. You might have studied about, everyone might have studied about solving some linear equation or something. So linear equations, studying connected to determinants and all those things. So you do determinant, but when the determinant is zero, it's a different case. There are some cases which are considered special cases, they don't solve it, exotic case or something. But when you generalize the whole thing as a linear algebra, in the framework of linear algebra, then you can make statements about all equations, and you can state much more, and determinant will not be relevant anymore after some time. So you can talk about rank of a matrix in a different sense. And so what I mean is, when you study in a linear algebra, this solution and all those things have a completely different meaning. So for that, I can give you one example, which is a very nice example. There is something called, it's very important to study functions. When you talk about mathematics, it's important to study functions. So there is something called Fourier series, where if you have any function, reasonably nice function, it's a continuous function or something, but when you have a nice function, then you can expand it using cosine functions, cosine and sine functions, cos theta, sine theta. Everybody knows cos theta, sine theta in the 10th standard. So using that cos theta, cos 2 theta, cos 3 theta, this kind of cos theta and sine theta, sine n theta kind of, this kind of sequence of these functions, you can expand any function as some infinite series or something. So this is something called Fourier series. And this Fourier series is very important in physics everywhere. It's very important to study function. but then to do this Fourier analysis, it's a very, I mean, in function theory, it's a very messy thing to do. But when you introduce this, I mean, these vector spaces can be, as I said, can be generalized to infinite dimension or something. When you generalize that and introduce some inner product and other thing, then the whole thing, the whole theory can be, we can prove it in within 1 or 2 pages. I mean, it's something like introducing something called some orthonormal basis and other thing. All these things follow very naturally, and it's not just applied to this Fourier analysis or something, it's applied everywhere. I mean, I will tell you later some other application for this. So it can be applied everywhere. So this is what is about modern mathematics. Modern mathematics is kind of subjects with, I mean, we define few things with some axioms. For example, probability is a very old subject. People have been talking about probability. But in the last century, Kolmogorov defined probability using some set of axioms. And he defines probability. Then there are sequence of theorems. We get a lot of theorems, and there is a ocean of work done on that. And that is applicable everywhere. So that is what basically modern mathematics is. Modern mathematics is a framework with we start with the axiom, then we make statement as theorem, we prove it, and I mean that's not much related to computation. It can be used to computation, but that's what modern mathematics is. So this maybe after discussion we can talk more. But so this modern mathematics is, I think it's, I'm not very good at history. Hilbert led this drive for this modern mathematics. You said something?
Yeah.
Hilbert. No, you can ask something. I'm sorry.
Yeah.
I didn't go.
No. I just wanted to say. Yeah.
Did I divert somewhere? You asked.
No. It is perfectly fine, Vasan. So if I were to say, mathematics is about that a logical basis for everything, and that nothing should be logical, right? So every
there shouldn't be any. I mean, it's not just illogical or something. I mean, we may be talking logically, but it's a very precise statement.
Okay.
There shouldn't be no contradiction. It should not lead to any contradiction.
Okay. So it is one. It is also very much closely related to logic, and secondly, it is also related to ideal objects which we take from the real world but make ideal. As you said, the concept of a length or anything, we idealize it with an idea. It is mainly an idea. When we measure it, we can only do it approximately, maybe, but not at the precision that the object would give you. And thirdly is the concept of abstraction, which you mentioned, which is that instead of studying just one function or let's say as a vector space,
collection of functions
as a vector space, it goes beyond vectors, includes matrices, and then therefore at an abstracted space you start proving theorems, and that applies to multiple fields at the same time, right? So that is one. So my other question, following up with what Rajmohan asked you, is when people talk about mathematics mostly, I just saw a tweet just about 3-4 days back in Twitter, where somebody asked, do you really use algebra in real life type of thing? We are talking about normal algebra, right? X plus Y, whatever, that type of algebra. But let's look at the fact that people understand the need for computation, need for, say, statistics. Nowadays, big data and all have come, and people are quite clear that statistics is very much needed for us. But when they hear something like abstract algebra, group theorems, or algebraic topology type of a thing, right? Do they will all feel, right? What is the use? That we'll come to the question of usefulness later. But how is it related to real life is a question that many may ask.
So Suresh, I mean, actually, before Vasant and Arul starts, what Vasant has been so far telling, it's very lucid, very clear, and it is very surprising. I don't know, maybe Arul Selvan can throw light later on in the discussion, that whatever he is telling, right? Pythagoras said that everything is mathematics. So from the inductive logic of counting, we are seeing 1 oranges, 2 oranges. When they say, when we see 1 apple, 2 apples, what we are seeing in orange and also in apples or any other object, there is a pattern recognition and symmetry. I mean, it's all from the ancient times. Even like we had Leibniz, we had a Kant, we had Nietzsche, all the even modern philosophers, even Goethe, poets, everybody had talked about importance. Whatever most of the things which Vasant is telling is very much available with us. I'm really wondering why this happened that most of us, I don't know, maybe some kind of a mystery aura was put around mathematics. So sorry, please go ahead. Please go ahead, Vasant.
Okay, no, I forgot the question. The basic question asked.
Suresh was asking.
You were asking something. You were asking.
No, I was asking that in a modern case, people may.
No, the use you are asking.
Yeah. What they may say, what is this usefulness of say algebraic topology or
first? First, you should say that it's an intellectual pursuit or something. Correct. But the use is very much there. I mean, everybody is using it. I mean, it's not something that people don't use it. For example, you talk about statistics. Statistics uses many theorems in probability. And that probability, see, first of all, I mean, there are theorems proved by probabilists, so which are used by statistics. Without that, we don't know why that is true. I mean, they may not be directly, I mean, without that Kolmogorov axiom, we don't know why that theorem is true to start with. So if there is some loophole, there is some problem with the theorem, it doesn't hold in general or something, or if there is something, that problem may creep through the whole thing and then everything may be wrong. I mean, you cannot use it everywhere, see. So for that, there has to be a security for that theorem. Okay, I mean, for a fact you use, there has to be a security, and that is given by probabilists. That is being used by statistician. So even in applied mathematics or physics, everywhere. So I mean, it's clear. So that security comes through the axiom and the axiomatic way of proving. So maybe I haven't explained how do we use this axiom very briefly. I mean, very at the basic level. I will just introduce what are the axiom or something. So I said that mathematics is any rigorous framework can be called as mathematics, but there are not many rigorous frameworks. There is only one framework which is created, which is using set theory. So everybody must have heard about sets. They must studied in the school. So the sets are something you put a bracket and have any collection. That's what people say, and it's not wrong. But there are some problems in defining set, which I'm not. I'm not entering into that complication. So if you understand what is set, the basic assumption in mathematics, one assumption is empty set exists. There is something called an empty set which has no element, and such a thing exists. We don't know exists, but it's even you see, for example, if you say number 3, it's not clear why number 3 exists. I mean, you have to define a number 3. So you can define number 3 as a set having 3 elements, but there are many sets which have 3 elements. So which set you are going to call as 3? There is a problem. So you have to define. So only when you do like this, you can be sure that these things are correct. Okay, you want to say this is a precise way of doing. So you want to make things are correct. So you have to define, first you have to define what is 3. So how 3 is defined is you have to first define an empty set. You have an empty set. Then the basic axiom in mathematics is empty set is not same as a set containing empty set. You take an empty set, which is one element, put that element somewhere and put a curly bracket with that, parenthesis, bracket or parenthesis, bracket around that. So that is what is called a set containing an empty set, which is a one element set, which is not empty set. These two sets are not same. Once you have that, you call this empty set as 0 and this as 1. I mean, this is not needed. I'm not saying that this is not needed when you learn numbers or something. But when you want to rigorously define a number, when you want to define 2, 3, you have to go like this. Once you have 0, 1, then you can define 2, 3 using this set. And you have a precise definition of 3. Then there is something called a bijection. You can identify this set with any other set with 3 elements. There is something called a bijection where you can identify things with. So that way you can define natural numbers. Then you can define rational numbers. Then using some construction, you can define real numbers. All the whole mathematics can be developed with that. So this is so these things are done by, do you want some name who did all those things? I mean, there are Russell, Whitehead, Hilbert gave many of these axioms, but then there is it's not that mathematical framework is complete. I should mention that there are some problems with that, in the sense that you cannot test whether, if you make any statement, there is a basic question. You make any statement in a mathematical framework or any framework, can you always whether you test whether, I mean, is there only two things true about it, whether it is true or false, whether we can test it. Test it may not with whether we have the technology to do that, whether it is possible to do that. So then the Gödel came with an idea that it's not that in any framework there will always exist statement which can never be decided whether it's true or false. But we don't worry about it because the basic thing, we don't get into those problems when we do mathematics. So when we construct objects, those problems will not arise. Okay. So the basic thing about the mathematics, you might have heard about proof by contradiction. You want to prove something, you assume the opposite statement, prove that is not, that lead to some contradiction. So since mathematics cannot have a contradiction, so that original statement should be false. So that is a kind of proof by contradiction. So so when we can do all that within our framework, we don't enter into whatever the problems with Gödel has created. That is something like we cannot, the basic idea first, we cannot handle infinity. I mean, there is some sort of infinity, because when you look at that, Gödel's proof is very complicated, but Turing has given some better proof of that, which you, from that you can actually understand that proof, where it's like something like we cannot handle infinity. Maybe God can handle that, but so it's basically that. So I was talking about sets. So it started with sets. So you have empty set. You can, using empty set, you can do that. Then you can make union of set. Making union is something like, it's like or, I mean, that everybody might be knowing. It's like or statement, this statement or that statement. That is what union of set. I said precise something like if there is a negation of a statement, the negation of the negation should be the original statement. I said you formulate a statement in terms of the set. Then there is something called a complement. You can take in you have some sort of universal set where you can take a complement. The point is the complement of the complement is the original set. So if you make statement in terms of set, then you get, if you make the negation of the negation, then you get the original set. So that is how when you make everything in terms of set theory, it will work perfectly. So that is why that is how the mathematics works. We work with using these things. Then there is some important axiom. The whole mathematics has an important axiom that if you have a collection of set, then you can choose one element from each set in an ordered way, which is something that which may look very obvious, but it's not clear. So when you have an infinite collection, when you have a finite collection, you can choose one element from each set, which is very much clear. You can choose one of them and then finish it. But if you have an infinite collection, even when it is there are many infinities. I mean, there is something called countable infinite, then uncountable infinite, something more than that. So when you have uncountably infinite or something, this is not clear. How you choose one element from each set and you form some sort of ordered pair is not clear. I mean, not ordered pair, some tuple kind of infinite tuple kind of thing. How you can make it is not clear. This is what is called axiom of choice. This is something which is assumed in mathematics. And people say that they need not assume mathematics, axiom of choice and do some mathematics, but that's not usually considered as mathematics. All mathematicians assume this axiom of choice. This looks like something very obvious, but then this lead to some very, I mean, for example, there are some very exotic sets and all you can create using this axiom of choice. I mean, there are in measure theory or something, there is some very complicated non-measurable sets or something. I mean, there is something measured. I talked about length or something, measuring or something sometime back. So what are all the measurable things? Any subset you can measure. What are all the measurable things? There are some very complicated measurable sets you can create using this axiom of choice. So the axiom of choice is not something very obvious. So if the axiom of choice is true, something very exactly you can actually create. So that's also you have to accept. I mean, if this is true, that is true. So something like that axiom of choice is accepted, and that's what being generally considered as mathematics. Okay. So finally, I want to make a point to say that we make this basically all our logic comes through set using this union and intersection and all these things. But there is something called a quantum logic where these things will not work. So what is quantum logic is something like the quantum mechanics. You know that every an electron or something, a particle can be in superposition. It can be in it's something like there's something called a super. It does not have a determined position. It will have a superposition, and so you cannot really. If a set means you have element, and it's like something like everything has a position kind of thing. I mean, if you want to logically develop a classical mechanics in terms of set. So in that, then the quantum logic has a, see, if you assume the set theory, there is something like, everybody must have studied in our high school, there is something called De Morgan's law or distributive law. So this distributive law will fail when you want to use quantum logic. So these things will not work. So some time back I talked about how to generalize a vector space and get some infinite dimension space called some Hilbert space or something. We have to use that Hilbert space. I mean, you can assume vector space. You can take a vector space and you can use the subspaces of that instead of sets. There, this distributive property will not work. I mean, this is just to mention that how so vector space you create for some reason will work for some other. I mean, to use the quantum logic, you have to use those vector spaces for those logic. You can use that and or statement in that, and all those things you can make, and that is what we should use for the quantum logic. So this is what. So I have said that, I mean, there is rigor kind of thing in every, I mean, in every field, every science, people try to formulate a statement by observing something and then look for counter-example, whether it is true or false. That's what they do, and then form a statement. Then they try to prove it, kind of thing. In maths, you can prove it. I mean, in physics also one does this, but then physics, you have to use mathematics to prove a law. But if there is a problem with the language you use, I mean, if that particular mathematics is not the right language, then the law will not hold after some. I mean, when you prove it using mathematics, it's secure. I mean, the theorem is true and the physics law is also true. But then the mathematics language is not the right, that mathematics is not the physics. Physics is something else. It is just the language. So when that is not the right framework, then the law will fail. That is how the classical mechanics will fail and you get into, I mean, quantum mechanics or relativistic mechanics, all those things.
Oh, okay.
So yeah, I think this is enough for the introduction.
No, I just wanted to check if Arul Selvan has anything to add here.
Yeah, sure. Yeah.
Before that, there seems to be a network problem with all the four of us. First, Arul Selvan had a problem briefly. The video of Suresh froze. Then now I have encountered.
I also, when you talk, I'm not hearing everything. It's breaking actually.
That's what now I am also
hear what I was saying.
Yeah, sorry.
Yeah, your voice was breaking.
Yeah, sorry.
Can you hear me?
Yeah, I could hear you now. Yeah.
Am I audible? Yeah.
Yes.
Yeah, you are audible. Yes.
Okay. So after such a long introduction, there's hardly much to say. But going back to the original question, I think the question is that what is modern mathematics? Vasan gave a mathematician's point of view. I will just try to see what I can understand, what an engineer would look at as a characteristics of modern mathematics. Like any other science, a lot of abstraction is involved, as he said before. So two distinguishing features that as an engineer I feel in the modern mathematics is, one is the abstraction part, the other is the structure of it. Both these define in a way as characteristics of the modern mathematics. That doesn't mean that the older mathematics does not have it. The older mathematics does have it. It also does have it, but not in such a rigorous fashion, so that you can move the ideas across fields of inquiry within mathematics itself. When it comes to physical sciences, well, the semantics is fully different. Like in say physics, the meaning of a mathematical equation is different from what a meaning of mathematical equation in mathematics is, if at all there is a meaning in mathematics. So that's a different philosophical question altogether. So when we take abstraction and structure as defining characteristics of modern mathematics, let us see more concretely how it reflects in the engineering field. Take something as simple as an extension of a material, which is defined, as we all know, Hooke's law, which is just proportional. That is, the more the force you give, the more it extends. Take a wire, just pull it from both sides. The more force you give, the more it will extend. Rubber band is a typical example. But the proportionality there is slightly not easy to define in a case of rubber band. Whereas in a metal wire, like a steel wire or a copper wire, it will, to a large extent, will be proportional. This is as we can see, an one-dimensional example. That is very easy to visualize for anybody to experiment, to measure things. So the Hooke defined what is known as the Hooke's law, which is basically a proportional law. That is, more you give a force, the more it extends. Now, this is one dimension, but that is not enough if we want to define how, let's say, a cubical thing will deform. Basically, let's say a cube of jelly, if you take and press it, how does it deform? Or for instance, if you take, I mean, we all know how the murku making presses work. If you take something like that and then press it, then you get the save or whatever from the bottom. Now, how the forces, how can you calculate the forces on the dough or flour or something? This is not easy with Hooke's law. You need something much more, slightly more complicated, because you press in one way, it tends to expand in the other way, and all sort of complications set in. So from one-dimensional law, you go to a three-dimensional law. And now the proportionalities are not easy to define, because in all the three different dimensions, there's resistance, which are different in different directions, which are different in different parts of the body, which the engineers call as anisotropy and inhomogeneity and things like that. Yeah. So basically what we have gone into is a very complicated system of measurements. So what exactly defines the way the material will respond to a three-dimensional force is what an engineer wants to know. If you want to build a bridge, for instance, you need to know that. If you want to know how to squeeze a metal into various shapes, you want to know that. So these are very practical problems which engineers want to understand. Now, this kind of generalized three-dimensional force to reaction, that is the stress to strain law, involves what is known as a compliance tensor, which is a tensor quantity, which is a mathematical object again. Now, this object is not seen in one-dimensional situations, or it is seen but it is not felt. So you need to have a kind of abstraction to go into three dimensions from one dimension, and some 2 centuries of mathematics to understand this easily. So modern engineers stand on some 3 centuries of mathematical rigor and the modernity, which we use it on an almost daily basis. Every undergraduate student of engineering studies this notion now, but it is not easy to get to this notion without an understanding of the abstraction and the structure that modern mathematics has brought in. So the abstraction is basically, as Vasan was talking before, even the numbers 1, 2, 3 are abstractions, because you can count goats with it, you can count cows with it, you can count apples with it, you can count redos with it, planets with it, or whatever it is. So one has got a meaning of something else. It can mean anything. Because of that simple abstraction, we are able to do addition on goats, addition on redos, addition on planets. We can do subtraction on them, we can do multiplication. So these are the structures that are imposed on that, which somehow we can formulate into easy laws. So that way, the modern mathematics as it is defined is a kind of a development which is closely followed the applications of science or carpentry or buildings, architecture, painting. So almost every human activity from the initial stages to now have both an engineering and useful aspect of it, as well as a mathematical equivalent to it. Suddenly you see that mathematics has gone too far, there is no applications and things like that. But that is, I feel it's a momentary thing as far as the history goes. It hardly takes a few decades for the science to start using it. And so the old notion that mathematics is pure and it is it's very remote from reality and all, they do not stand to scrutiny anymore. Many times it's engineering which has driven mathematics. The whole of Fourier analysis, which he was talking about, was totally a science and engineering driven field of mathematics, which of course later on goes into abstraction into mathematical analysis, a whole area of inquiry.
Yeah.
So in a way, mathematicians do the cleaning up act for the rest of the sciences, and they give a consistent language which the others can use with confidence, basically, that they will not be wrong when communicating with others. So it gives a clear language to communicate, and also it gives a confidence to the other scientists and engineers to say that what they are going to do or they're saying makes some sense, consistent sense across the participants. So that's a very short introduction that I wanted to give. So we can go to the next question.
Yeah, thank you. I'll also just add one thing. Like Arul said, a couple of examples which I could think of where mathematics had solved a problem, which was later used by engineering. One could be in electrical sciences, especially when you do electronic circuits and all. You get a second order equation, and that to solve that, you require complex numbers, right? You require the whole equation is solved using e to the power I theta. So this was already solved by people like Euler and others. So when we now today assume a solution for many of the electrical circuits you draw, electronic circuit that you do, it is something which happened 200 years probably before the actual problem came up. So mathematics had solved that problem for you maybe a couple of 200 years back. Same way with, if you look at quantum mechanics, the problem of non-commutative matrices, which troubled Heisenberg a lot, that was already solved in mathematics. So somebody actually asked Heisenberg, why are you trying to solve the same problem again? Because much before quantum mechanics came, those sort of problems were already dealt with. So as Arul said, most of the time mathematics is always ahead of engineering and physical sciences, and sometimes we catch up within a decade or two. Sometimes it may take a century or two to catch up with what mathematics has done. Okay. Yeah, Rajman, I think.
Yeah. So basically, I will allow to start with Arul. So we see that, for example, equations, people encounter problems in real life, and then they write it down in a paper, solve it. So it helps them to some kind of a project. Whatever the issues are there, they can solve it. But when it comes to that, this modern mathematics, you say that from reality, you take it and make it as an abstraction. But what kind of a utility will be there for the mathematics, modern mathematics in education, especially higher education? So what kind of utility or usefulness of teaching mathematics across spectrum?
One thing is that I would step back and look at the teaching itself. The point is that, of course, I hold the view that anybody who wants to learn anything should have access to that, which simply means that irrespective of what the use is, one should teach it. See, knowledge for knowledge's sake or whatever it is exists in the sense that one is curious to know something, so he knows it. He attempts to know that, and then if he's successful, he knows it. So there is that way we create knowledge. To pass it on to somebody, then that is we require an audience, so somebody who wants to learn it, so you would pass it on. So irrespective of what the utility is, this endeavor in humankind goes on. Somebody learns something. If somebody wants to learn it, he teaches it. So this seems to go on without anybody thinking about whether something is useful or not. The useful part comes in when the system, that is the society, wants to make some activity of its members as productive. That is irrespective of whether it is what system of governance is, whether it is capitalistic or communist or socialist or dictatorship, it doesn't matter. They all set some sides that our society should go in this particular way. These are the areas in which we want to contribute more. These are the areas in which we want to develop more, or something like that. So the society sort of has a underlying understanding that these are the ways in which we want to progress. So these policies are set such that these are the kinds of knowledge that will be taught. So the schools and colleges tend to teach these things. The kinds of knowledge that which at that particular time people want to see whether it is productive for its citizens or not. So the usefulness is one part. The other part is the communicating the knowledge per se. So these are two different aspects. So I think I'm slightly smudging the issue into saying that usefulness is not the priority, but it is not so. Let's say, take for instance, these days everybody learns data science. Sometime back it was not so. It was academic curiosity. Some 20 years back, people are doing a lot of big data analysis, but nobody called it a science by itself. And nobody, I mean, physicists were doing it for ages. But now it looks like every street corner will offer a data science course or artificial intelligence course. These are like new typewriting institutions and shorthand institutions. Anybody will become a data scientist. Anybody will become an artificial intelligence.
Oh, okay.
I'm not saying that these are to sort of keep them down. I mean, show them down or something like that. But the point is, suddenly the society decides that this is the way we want to go. This is the way the opportunities are. This is the way the knowledge is knowledge is progressing. So everybody jumps onto that. This is the government wants it. The academic institutions want it. The teachers want it. Students also want it. The industries want it. On the other hand, and so this looks like a kind of what I can say, psychological state in which suddenly societies shift from one to another. So we define what is useful, what is not useful. Science as such progresses by acquiring knowledge and then communicating it.
Yeah, but because Vasant, okay, you listen to what Arul said.
Yeah.
Yeah, but you know, even 30 years ago, 40, at least till mid-70s, whether you are pursuing engineering, commerce, economics, literature, at least in Tamil Nadu, people are taught logic, both Aristotelian logic and mathematical logic. So it, in a way, it empowers the student, it creates a good society.
Yeah. So what is the question?
Yeah, it's for you. Yeah, please.
No. What is the question? I didn't
The
understand.
question is, I mean, will it not be more useful for the to teach this kind? Because when I listen to
That is no. That's this kind of no. I think this kind of when you teach something, when there is some kind of courses in the university, asking this question of utility itself is I think it's a kind of vulgar question. I mean, it's not you are asking. I'm generally saying that this is useful or something. You can. It's not just mathematics. You even talk about anthropology or anything. You cannot just determine how it is useful and kind of restrict the idea of usefulness. There is nothing like, I mean, an anthropology can be useful if you learn anthropology and it may be useful to our whole human civilization. It's not clear how. It's not something that usefulness means you increase the GDP or something like that. I mean, it's not that everybody becomes an engineer or whatever. The usefulness may be in a company. Getting a knowledge itself is useful to start with. As Arul says, that itself is to start with. That is the usefulness. On the other hand, you can no way guess what is useful, what is not useful. I mean, even the material use also, if you look at how something, as Suresh was also saying, that how something which was done long back is useful in quantum mechanics now. And I mean, then for example, you can even ignore the quantum mechanics itself. That science, we don't need it. I mean, why do you have to know what is an electron doing or something? But now there is some quantum computers are being done, and I mean, that way also you cannot guess. I'm just saying, first I'm not accepting that idea of usefulness, but even with the restricted meaning of that usefulness, if you use that, then also you can no way determine what is useful, what is not useful. So I heard that in some communist regime, quantum mechanics, quantum scientists were arrested or something. But then for quantum mechanics is, I mean, nowadays we talk about quantum computation and all that, and everybody says in next 10 years we will be having quantum computers, and that will be, I mean, that will be the natural thing to happen. So that way, that whatever you call as utility, it comes from something which you thought some time back it's not at all useful.
Yeah. So before I ask Vasant the next question, I just want to make one small observation. Somebody said that, about the same thing which Vasant said, that if you think about only usefulness, you'll never get into something totally different, right? Somebody said that if I kept on asking my customers what they wanted, they would have wanted a faster bullock cart. Nobody would have dreamt of airplane, right? So that's how it becomes. So now, Vasant, question to you. Now, as you said, right, the fundamentals of mathematics are based on a certain logic, axioms, and ability to understand the abstract nature of it, right? So do you think, given the current education that we have and the mathematics that we teach in school, what do you think is the right time to introduce these sort of concepts to the youngsters? Because what happens is all they're learning is a standard mathematics. Though they are told about limits, they're not really they understand what's the significance of that. They just by heart the dy by dx formulas. And once you come out of that trigonometry and calculus into something like group theory or topology, it looks like something completely different to them. So how do we, what do you call, smoothly transition this?
So no, well, I don't think we should introduce axiomatic mathematics in high school or something, in the sense that, for example, we see, for kids, we don't really teach the grammar of a language. They learn the language by itself. I mean, we just talk and they learn the language. It is not that we teach the grammar of a language and then they learn it. So it's like mathematics, they need not learn, I mean, even others also need not learn. Even for people doing research in mathematics, they need not really learn the Bourbaki. I mean, they need not have read Bourbaki. No, I would advise everybody to go through Bourbaki for some time, for a short time at least, because to get that experience. But for anybody doing research, not others. But even researchers, they need not do that, because we do. I mean, it is just we get used to that language without even really kind of understanding. I mean, I need not know the grammar all the time when we talk some language. We get used to it. So, but then there will be a referee, somebody, if you make a mistake, somebody will find it to you and explain it to you. That's not a problem. So I don't think that, if we start working with a very abstract thing, they may get some, they may not, the interest may be lost or the purpose may be lost. Say, for example, the purpose is you have to do some mathematics and but I think that rigor has to be there. There shouldn't be no memorizing or something. The calculus should not be taught the way it is taught. That I'm sure about it. When you talk about limit is not some sort of substitution. They have to know that limit is a limiting process. One should know that. And there is one of the very wrong notion is about integration. For example, people think that integration is a reverse process of differentiation or something, which is certainly not true. They should know that integration is a kind of generalization of summation. You want to sum something, you sum finite things, you sum infinite things. When you want to sum continuous parameter, that is what integration. That's what they should know. Or they should know at some point, then they should know the fundamental theorem of calculus, which connects with the differentiation. So that is what one should know. Otherwise, they should not. There is no need to learn integration. I mean, it is just you guess what is the derivative of this, then get the integration. I mean, that's the wrong idea. because the wrong idea gets into mind. Because I interviewed some students who have done BSc, MSc, they haven't really understood what is Riemann integration. Okay, so this is because at the very young age in the higher secondary, something gets into that mind that integration is some the reverse process of differentiation, which is something terribly wrong, which is not correct. I mean, so it's only fundamental theorem of calculus connects those two things. So those kind of things certainly should not be there, and there is some amount of rigor has to be there in terms of, you need not say epsilon delta, but you should give enough example to demonstrate that limit is something, a limiting process, not exactly huge. I mean, you can only substitute when something is continuous. You cannot, limit is not a substitution. Limit is, I mean, that's how people compute limit. It's not something like that. You have to understand the limiting process in some sense, some way they have to understand it. There should be I mean, we can give examples, how to understand it with you need not give the proper definition, you can give examples. So some sort of rigor has to be there. There is some problem with the way they are teaching, but this is a basic problem with our education is, see, in my opinion, somebody scoring is 60% or 70% should be a good student. But then we see somebody scoring 94, getting 94, and then they're crying. I mean, the 94 seems to be their life is lost or something like that. So we have a terrible education where you have to score 94. Then you will they will end up with this. So that's some people say not that everybody has to understand integration. They can do some other mathematics and pass the course. That's okay. I mean, they should also survive. It's not that everybody has to understand. But when you introduce integration, you have to introduce properly. So, but people want to score marks, and you have to. So that is why the general understanding is mathematics means memorizing, and then you solve some problem. It's like that. So I think some change is needed, but I don't think the abstract idea of maybe some use. So you can introduce, for example, matrices. Matrices. When you introduce matrices, you get the idea of non-commutativity. See, people don't understand what is non-commutative. You don't have to say that real number is commutative or something, because whatever we see, everything is commutative. When you see non-commutative, when you look at matrices, so non-commutativity is very much there, and you can talk about matrices as a whole and talk about algebra. There is something matrix, collection of matrices and collection of real numbers share between them. You can add both of them. You can do something. You can multiply by scalar. There is something happening. So you can say such things can be. I mean, I think group is introduced in higher secondary level. Is the definition of something?
I doubt.
I don't know. When I was doing my +2, I don't know the definition.
No, not at least. In Karnataka, +2 group is not introduced.
It was several years back, so I don't clearly remember. But
maybe Arul can tell us something.
That's not necessary. But what I'm saying is this axiomatization, all those things you need not impose on them at +2 level. You can learn it. There is some amount of rigor has to be there. Anyway, Arul, continue.
Yeah, Arul, you please go.
I want to say something. This let's take something like as simple as a group. Group can be easily introduced through the notion of symmetry.
Right.
Symmetry is indeed introduced in high school. Basic crystalline structures, for instance, are introduced in schools. Along with that, it is very easy to introduce a notion of symmetry with the definition of a lattice. It is not impossible to introduce higher mathematical ideas like groups into the school curriculum itself. Even notions like topology can be introduced if in terms of counting holes. These are very elementary intuitive ideas which are not very rigorous, but still they give the flavor of what it is. Euclidean geometry itself is a fantastic way of teaching mathematical rigor because it teaches you what proof is in a very rigorous fashion. So we all learned Euclidean geometry in our 9th, 10th classes. I don't know whether it is taught in such an exhaustive fashion nowadays because the syllabus seems to be huge now in schools. But we were taught almost whole of Euclidean geometry, 2-dimensional, 3-dimensional geometry. And it gave a fantastic foundation for an idea of what exactly is proof, meant by proof in mathematics. So that gives a kind of intuitive training to you. Same way, a lot of higher mathematical ideas can be introduced at a very young age, provided somebody takes the effort.
Induction is something introduced in +2, I think. So there is a proof.
Yeah, takes the effort and then makes it very concrete. I mean, only some people can take a very abstract view of things and then stay there and then stay consistent there. The way children learn are quite diverse. It is not one way street. So the teacher has to be very sensitive to the students, and then try to teach it in different ways. I mean, I don't think purely defining the lemma, theorem, statement, axioms route is fit for teaching everybody. Only few people can go take that path. The others, they are not less than the others, less than the people who are in the first category. In fact, they can be much more productive even in higher mathematics. These are very subjective ways in which student learns, and there are set of ways in which a teacher can approach that. Some people understand very concrete examples, some people understand very abstract examples. So you can teach higher mathematical notions which are created in 20th century, for instance, even now to students, high school students. But it takes a lot of effort. It takes a lot of dedication from the teachers to be very sensitive to the students, and never to grade them on these things very strictly, which I would say is a very important point in learning environment, in creative learning environment.
Sure. So actually we are we may not have time within this to discuss that, but one of the key things which was highlighted by Arul is also the fact that that this also requires not just the change in curriculum, but change in the approach of teachers, and teachers themselves getting trained and understanding this, because even teachers understand only the standard method here of by hearting the theorem and telling that. So the amount of training that needs to be given to teachers also be substantially high. Yeah, Rajmohan.
Yeah,
sorry.
Basically what Arul Selvan and Vasant, they are telling that it's they made it very beautifully what modern mathematics is. What is is there any huge contribution from Indian side, Indians contribution to modern mathematics?
So
like we heard about, recently there was a news about Seshadri, when he passed away.
So in my opinion, there is some regular contribution coming from some of the elite institutions, but in a sense, India is, when you compare with Europe or Japan, or I think India is not, see, the basic problem in India is our universities are not contributing. See, there is we need to, there is some sort of, I don't want to use some words, but there are some mathematics happening in the elite institution, and it's not happening in many of the universities. Especially university has some other things I have seen. There are very good people doing some other, even chemistry, biology, and all those things. But some more mathematics, there are not good research happening in universities. So even if you ask for contribution from India, I don't. So there was a talk that Seshadri, the Seshadri Narasimhan theorem or something that could have got them Fields Medal or something, but it was not given or something like that. But other than that, that kind of mathematics contribution, I don't think has come from India. There is, of course, there is Ramanujam and thing, but there is a very regular, very concrete contribution has come from India in most of the field, like harmonic analysis, operator algebras, algebraic topology, algebraic geometry, and most of the subjects. There is some very continuous contribution coming from many people here. But for example, I can talk about someone called K.R. Parthasarathi, who has founded a subject called quantum stochastic calculus, which is he is one of the founder of the subject. So, and of course, you heard about Seshadri, and there are others from in number theory and other things. There is a very good contribution.
I think even in ISC has a lot of people, right? Mahalanobis and Varadan and all that, statistics.
Yeah. No, Varadan is not from India. He's okay. Then, if you want to count people who have gone abroad from India, Varadan is not in India.
Okay.
If you want to count, then there is a lot of contribution. If you want to say,
no, but from institutes, yes, you are right.
Indian, but he studied in India, so he started in India. So there have been mathematics, of course. That is, you can't restrict to India. So people have gone from India and then contributed a lot. So so there is some very concrete contribution, but I think that all our university, see, for example, if you take any university, University of Kyoto or University of Tokyo, any Japanese university, some University of Hokkaido or something, in that university, there will be a seminar in any subject. Those people will not attend the other subject. Okay, there will be seminar on probability, means they will be attending. There will be each week there will be a seminar on probability thing. But even in our institutes, there are no seminars happening in one single subject each week or something. In all our whatever this math science or wherever we have, it's true that there is no seminar on there is no seminar each week on operator algebra or something. Okay, there is not that many operator algebras in India, so that we can do that much operator algebra. So that there is not that many people we are having. But there, each universities run their own, each subject they run their seminar. They don't attend another seminar. So here I have to attend a seminar. I will attend a number theory seminar. It's good. That's a different issue. But the thing is, there are so many people, and that much contribution is not coming from India. There is no doubt. There are some very good contributions.
Okay. Because Arul, what Vasant was telling, I saw that global indices for all the countries across, and research in mathematics, we are ranking so below, and application of mathematics. So why do you think so?
Well, I don't know why pure mathematics we rank so low. See, we were hardly, take chess for instance. In 60s, we hardly had an international master. Now we have 64 grandmasters. How did it happen? I mean, that's as abstract as you can get. And one doesn't understand, for a country of size India, why we have so little contribution in mathematics, which hardly requires any infrastructure from the university to provide. They all need is a desk and a blackboard and supply of chalk pieces. But still, it's really a mystery to me why we don't contribute so much in pure maths. In applied maths, it's a different thing altogether, because most of the engineers nowadays are, I mean, I shouldn't say nowadays, some decades back, they were quite trained in mathematics. But nowadays, everybody goes into simulations, computational mode. So the emphasis on the analytical solutions, analytical problem solving has gone down. Now everything is simulated, everything is computed. So the rigor which is required in studying the pure parts of mathematics, the necessity has come down enormously. People use numerical tools to simulate whatever they want. So there is certainly a difference. This is not confined to India only. This is all over the world. It's the same thing. That is, people tend to simulate and then do modeling and simulation much more preferentially than do the analytical solutions, which is tough to come by anyway. It is not easy to. You spend a lot of years and you may get a solution or not. Nobody can assure you that. And there are pressures from academic side that you have to finish this much and you have to publish this much. So this is a kind of vicious loop. But I would say, as far as the computational aspect goes, simulation aspect goes, we are doing very well. There is Indian engineers are quite talented in that. Even in our government labs, we have fantastic people who can do a lot of things. But well, I can say in analytical side, we are lacking a lot, even in engineering.
Suresh, what Vasant and Suresh, what Vasant and Arul selling is very sad, actually. Even in other fields like philosophy, sociology, economics, our research actually is going down. I mean, I don't want to use the word plummeting, but in humanities, it is.
Okay. No, I wanted to ask Arul one to expand on something which he had once done a small tweet thread. He had spoken about the gap in mathematical education not between India and other countries, but between the state-run colleges of India and some of the central universities like Ashoka or other universities. Can you expand on that, Arul, which you had once spoken about?
Yeah, actually we have covered that a little bit now, both Vasant and me. I don't know much about the university's teaching part, but I just went through the syllabi of various
Yeah, that's what I was
universities
mostly
and
talking
tried to
about.
compare them. What do they teach?
Yeah.
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 What they teach. The state universities, I compared, let's say, Karnataka, Tamil Nadu, and Maharashtra. The state university syllabuses did not have a course on, let's say, something as good as topology, basic course, or algebraic geometry, or differential algebra. So the point is, the whereas the central universities, the ICERs and then the other things do have very rigorous undergraduate programs. I wonder why, whether the university senates do not push for such a high quality teaching and research in their own domain, or where is the lacuna?
Laxity, yeah.
Policy level or implementation level, or encouraging people to do this. Most of the times the pressure should come from the students themselves. They can ask for certain electives to be given in particular specific fields. But I wonder how much the students themselves are motivated in the universities. I can only remember when I was doing the undergraduate level, some of us got together and then went and demanded the department should give this course for us in the next semester, and then we got it through. Such kind of motivation from students is also necessary to go and demand. But again, it is I don't know where the problem is. That it looks very intractable for me. But I can see very clearly that the universities, state universities, are not up to the mark in terms of even basic formulating the syllabus to the requirements of even postgraduate engineering education. Postgraduate engineering education requires good amount of mathematics, rigorous analytical mathematics, even today. But I don't see even the math departments of universities offering that level of competence in their undergraduate levels.
Okay.
So there is a problem. We have to go to the individual syllabi in detail. But I can clearly see there is a problem.
Okay, so I can just, as a follow-up, ask Vasant, if you see this problem when you try interviewing people to take into your postgraduate or...
Sure. Yeah. So they have some problem, but there are people who come from universities and they do very well. And see, these days there is this internet and they can listen to some lectures from Princeton or something on the YouTube. So
Correct.
there are some, so out of that interest, there are students. See, there may be some student in Tuticorin or Tirunelveli, where I come from. I didn't do that at that time, but who can come from there, but they can listen to everything in the internet. They need not rely on that if they are interested in mathematics. So there are some people we see some such phenomenon also, but in general, those who have studied in universities, see, I see that there is a basic problem in analysis. There is some algebra analysis something. See, they are able to somehow study algebra. There is some algebra, and somehow the understanding analysis, they all have some problem. That's what I have been encountering with many of the students.
Oh, okay.
So I have to understand why that is the case. I mean, because there is not possible to memorize or something, it's not clear. Algebra, you just have to do some algebraic operation and then do something and you get it. Analysis, there is some kind of, I will not say what is creative, what is not creative, but analysis, there's a serious problem. That's what I see with many students.
Actually, actually that I wanted to ask something very layman question to both Vasant and Arul. Vasant, anything that is, there is a theorem, a particular theorem, how it gets tested? Is it tested in reality? You said ontological status.
No.
Very clear.
So that's a very good question. So the thing is, see, in mathematics, theorem is tested, till now theorem has been tested by experts. So you should believe the experts, you should believe the system. The system is going on very rigorous or something, that's what one should expect. But nowadays theorems are being tested by computers. So there is a computer science, there is an area to test this theorem, and many of the theorems are already tested. And I mean, because human can make mistake, and it's not clear who will not make mistake. I mean, see, for example, there is an interesting case. There is someone called Michael Atiyah, who is a great mathematician, who got Fields Medal and other thing, who is a very great mathematician. But recently he announced that he solved Riemann hypothesis, and he gave a very vague lecture. And which has a lot of problems. How I mean, I shouldn't be saying this. I have a lot of respect for him, but he have a very vague lecture where it's not clear how a mathematician gives such a lecture. So it's, I mean, it's human being with old age, anything is, but he's 89 or something. So anything is possible. So how do we trust? But then it's not clear how youngsters are so perfect or something. So human things the human way of testing is not reliable. But as I said, that problem is always there with mathematics. But so they decided that there should be a computer way of checking these things, whether the theorem is true. Still, I don't think computer can prove theorems, but I think computer can test whether a theorem is true or not. And that way, many theorems are tested. So I haven't studied how it is done. I'm not sure, but I know that's happening. There are many theorems are tested, and it's true. That is one answer.
Okay, sure.
Arul Selvan.
Yeah.
Sorry, Suresh. Go ahead.
No, I think you wanted to ask some question.
No. I just wanted to ask Arul what his opinion is.
Okay. I also wanted Vasant for you to quickly outline which are the premium institutes in India which actually are teaching mathematics, where recent amount of mathematics or statistics sort of research is happening, and reasonable contribution is happening. May not be path-breaking one, but reasonable contribution is happening in that field.
No, one thing is for undergraduate education or research education.
Both.
If you want undergraduate education, there are many ICERs with Arul was talking. I don't know about Ashoka University and others, but I've seen ICER is giving a good education. But the best institute, whatever it means, is considered is I would say ISI Bangalore is one of the best institutes to do mathematics.
Okay.
Chennai Mathematical Institute is also one of the best institute to do mathematics where I am working. But the thing is, with Chennai Mathematics, there is a security that it's not just mathematics; it's mathematics and computer science.
Okay.
So it's worth commercially also. I mean, so the parents need not worry about their life, children's life or something. So that way, it's a CMI is one thing. But I would say that the kind of education given in ISI Bangalore or CMI should be given in all our universities. There is no doubt about it. So then there are, all these ICERs, IISc, they all have very good, good education. But there is a problem that, recently I was visiting one institute, let me not say which institute, one of these ICERs or something. There, they all study the same thing in the first year. All the BSc students, it's a 5-year course. They study the same thing in the first year. Then they have to opt something. Then there is, of course, the competition and all that. The top level students, they opt for some biology, chemistry, and other things. Those who don't good marks, they go to mathematics. Mathematics is supposed to be difficult, but then there is no market value or whatever. But those who don't want to do mathematics are forced to do mathematics, which is really ridiculous. It's something those who are interested in mathematics should do mathematics. So this is the phenomenon I see in those ICERs and those kind of institute also, which is not a good thing. So that's what I hear. So for research, of course, TAFR is well known, and ISI, Math Science, and these days the IITs are also there. IITs were not contributing in pure mathematics, but these days a lot of people have joined IITs, and there are good pure mathematicians in IITs also, IISc, everywhere. This has happened in the last 20 years or something. There are good research is going on everywhere, and they are all contributing regularly, some reasonably. As you say, not up to the Fields Medal level or something, but there is a good mathematics going.
Okay. I think, we have sort of probably asked you all the questions. Just wanted to finally end with one particular thing that you told, and for which Arul Selvan has also started a blog, but he didn't continue, called the Bourbaki School of Mathematics. Can you both just elaborate a bit on what it is, and then we will probably close for today.
Yeah. Arul wants.
Yeah, Arul.
Oh yeah, no, actually that is a very interesting experiment. Not experiment. That is a movement. It started actually. Vasant will know much better. Uh, I came. I was forced to think about it simply because my mother, as a school teacher, was sent in the middle of her career to learn the set theory and then basic mathematics, modern mathematics to teach in schools. It was a difficult thing for me to see that teachers will suddenly get trained in an entirely different way to teach from the way they were being taught before. So I wanted to know what it is all about. So I started learning, reading about that. So then I realized that I was a student myself. I was a school student myself. Only thing is that I escaped that part because I was a senior by a couple of years. My brother got caught in it. So I went and read about it. So that's why I came about it. So it's all about what we talked before. That is the way of abstraction and structure. The defining theme of the 20th century mathematics is the structures, basic structures of mathematics, and identifying various mathematical objects and then see how the structures evolve. They sort of formalized everything and then started putting a very axiomatic way of pedagogy, which is not at all natural for learning. But it was very fashionable to do that kind of teaching in 60s, starting 60s. It started in US, then it spread all over the world. In 70s, in mid 70s, it came to India. At least it came to Tamil Nadu. So after that, it stayed. Even now it stays, even from 6th standard people learn sets, but it is totally non-intuitive. Why should anybody put a goat and then idli and then a bureau and a table in one set and then say that it doesn't make, it defines a set. So that's how a basic set is defined in a school. Why should you put unrelated objects into a bracket, in between flower brackets, and then call them a set? So this is all totally counterintuitive, but that is how it is taught, because that is how it can be taught. Then you go to real numbers as a kind of form, concrete realization of something. So it's all coming theory first, and then the examples, and then empirical ideas later. It puts kind of puts the cart before the horse.
Cart before the horse.
It cannot be so always. Young people need solid, concrete examples and empirical observations to
Correct.
drive curiosity. You can't drive them purely by abstraction. But it is not very unusual also. Some people can, there are one or two students in any class who are very comfortable with abstraction rather than the concrete things. It is simply the way the human mind is wired. We don't have to make much fuss about it. It is not that one thing is superior to other. Both are the same, sure, ultimately. So Bourbaki sort of defined this way of teaching, mathematical pedagogy. They came out with tomes after tomes, which are accumulated by all libraries, big libraries, and who have got funds. And then they expect people to learn. But one thing is that within mathematics itself, the whole of mathematics has got reformulated into that language, both in terms of notations as well as the pedagogy, because it is, in a way, it is the fastest way to learn a subject without much paraphernalia or distractions. I myself prefer learning that way. I prefer books which are very small, 200, 250 pages long, which go in an axiomatic fashion. But I would say that not people. It is not a general prescription for everybody to learn. Okay. But for practicing mathematicians, I think it is the way to. I mean, that is how it is done for the last 46 years.
Yeah, Vasant.
Interestingly, the empirical kind of mathematics came again into the fore in 80s or something with low-dimensional topology and things like that, which were very interesting for me because that has very concrete ways of teaching things. It came in a big way, and then mathematics, both maths and physics got enormously influenced by knot theory and other spin-offs. So it sort of hither and there. Vasant can elaborate on that.
Yeah.
No, it's fine. So I mean, more or less, Arul has said. I mean, so the Bourbaki started in France, I think. I mean, it's after the First World War. So there are 5 mathematicians. I think initially 5 mathematicians. Then a lot of people joined, and it became a movement. So I think it's André Weil, Chevalet, and Dieudonné. I don't remember others. So they started this and started publishing papers in this name and started publishing books and all those things. And it's a very, I mean, in a sense, they were making more better definition. I mean, it's, there are things which are already in the use for a long time. They were making it into proper definitions and proper theorems and going it in a very systematic way. And that is being, I mean, as we said, there has a tremendous effect and it's being accepted. But there are, of course, people accusing them that they are proving something which already has been proved by somebody. I mean, and then taking the claim that something like that also. There are, I think Arnold was very critical of this Bourbaki phenomenon. They destroyed mathematics or something. The thing is, they completely removed the mathematics from reality, especially from physics. So that is the accusation from Arnold, and so I think there are some criticism also, but I think that is needed in the sense that I think some people should do that kind of mathematics, and others should. I mean that's how it gives the security, as I said. The security is given by that, and then others. Not everybody need not learn that or work in that fashion.
Sure. Okay. So I think we are almost at the end of our allotted time. So let me thank both of you, and let me just quickly summarize. So we have tried to understand what is modern mathematics, and Vasant has given us a very good outline of the rigor that is needed, the accuracy with which you have to state a statement, and the negation of negation being giving you back the statement, and other criteria, so that everything is on a very strong foundation that you cannot disprove it once you have proven it. And then we went on to discuss various other aspects of mathematics and mathematical education in India. And we have now seen about the Bourbaki theory. And we also saw how mathematics relates to real world, as well as how its usefulness is there in multiple fields of engineering, and how to a large extent, mathematics will always be seen as an abstract field, which currently may not have the use, but probably as things develop on the other side of engineering, we will catch up to what mathematics did and use the mathematics of today. We may end up using that maybe 10 years later, 100 years later, we do not know. So with this, thanks for this fairly long session, and thanks for patiently answering all the questions to both Dr. Vasant and Dr. Arul. Thank you.
Yeah, thanks.
Very happy to be here.
Yeah, thank you, Vasant and Arul. So now what I'm going to do is, both of you spoke very well and very lucid and very beautiful. Okay, now I'm going to go back and learn more mathematics now. Okay.
Very happy to be here. Thanks.
Thank you. Thanks, Arul. Thank you.
Thanks.
Okay.
Thank you.
Okay.